Hello guys, welcome back to the YouTube channel of The Concept Guy, and this is the third video of the lecture series of process safety and the source models in specific. So today we'll first go through a simple question on flow of liquid through a tank or vessel, and so that we get to know how to actually go about a question. So first we'll go through that, and in the end we will actually start our flow of vapors through a tank. So first of all, the question is from Chemical Process Safety, the book called Chemical Process Safety, written by Daniel A. Crowell and Joseph F. Lover. It's a Daniel A. Crowell book, and in the fourth chapter of source models, there is a question. A source tank water contains water contaminated with small quantity of soluble hazards. So let's just, the question is, you can actually take a screenshot of the question in the video, and so you see that this is source models. Okay, so as per the question, we have here a tank. So this is a tank, assuming that it is at P atmospheric pressure, atmospheric vented tank. Okay, and this tank is 3 meter in diameter. So our dia of tank is 3 meter and height is 6 meter. Okay, height is 6 meter. Now what it says that at the current time the liquid height is within 1 meter of the top of the tank. So this, assuming this is our top of the tank, 1 meter height from here. At this point the liquid is 1 meter within the top of the tank. So from the top of the tank 1 meter, so from here we know 5 meters, the height is 5 meters. Next what we see is that there's a leak at the bottom. So the water will flow out from here, leak, and this leak has a diameter. So let's say DL, the leak diameter. It says if a 3 centimeter internal diameter feed pipe, so this is actually a feed pipe and it is 3 centimeter diameter, or let's take 0.03 meter. Okay, 0.03 meter, and what happens is that there's a leak and liquid will flow out from the bottom. So we need to find the liquid level after a time of, so after the leak, a time of 30 minutes have gone by, and after that the leak is operated or it is closed, emergency response is activated. Okay, so we have to find how much liquid level has dropped during this time. Okay, and rest everything is same, maximum spill, that is QM. So as we have seen in the previous videos of this source models, so you know we have to just start with our Bernoulli's equation. If you don't remember anything, if you don't know how to go about the question, just start from the Bernoulli's equation itself. We will start with the Bernoulli's equation. So first we will take 2 points where Bernoulli's equation could be applicable. So our first point is this, the top of the tank, the liquid level, this point, and our second point is the leak point. So these are 2 points where we will apply Bernoulli's. So P plus, this is pressure term, plus the potential term plus kinetic term, U square by 2 alpha. This is kinetic energy correction factor. So for now this is, let's say P1 H1 U1 P2 by rho plus GH2 plus U2 square. Now here we know that P1 and P2 are same, both are at atmosphere, so they will cancel out. Okay, and this H1 H2 will be nothing but the height difference. So for that we can take that H1 minus H2, let it be HL. Okay, height of the leak. Okay, and next from this, using all of these equations, we previously found out that our QM was something kind of rho A. QM is this, the mass flow rate coming out of the leak. So that is rho A into U bar. U bar, we know that the velocity of at this leak, U bar, because this velocity will be very low. So it was discussed in the previous videos. You can actually go through them and understand. So now this would be actually equal to rho into A. This A is the area of leak in particular. Okay, and this C naught under root 2 PG, let's say the PG is that ATM thing, and PG should be actually 0 here, right? Because it is vented. So PG is 0, and but there is some GH term, GHL. So this is our equation. So what is the basic thing that we have to do here? The mass flow rate that is decreasing here, like some of the mass is lost and that is coming out. So this mass that is decreasing and this mass that is coming out should be equal. So dm by dt, we have done it earlier, dm by dt is qm, right? Now m is, we have stated it, rho into v, rho into a into dh, and dt is equal to qm. So qm is rho al c naught under rho 2 ghl. So this rho could be cancelled out because it is incompressible flow. And finally we will integrate dh using this H2. So this is like DHL. So we will integrate both equations like this, DH upon DHL, let's say DHL upon under root of 2GHL is equal to C naught minus A L by A. This is area of tank. This is tank part, this is leak part, area of tank. And finally dt, this will go from, if we say that this will go from H, so this is 6 meter, we have initially at 5 meter, so at time t is equal to 0 we have 5 meter, and at time 30 minutes after we need to find out the height. Solving this equation where C naught is 0.61, we can find out the HL. Hope it's clear. So please write the answer of HL, the value of HL, in the comments section, and I hope you will find out it correctly. If there is doubt, I will again clarify it. Okay, hope the calculations are good enough. I hope theoretically there is no problem. So next we move on to the flow of vapors. Flow of vapors through holes. So unlike the flow of liquid through holes, in the flow of vapor, one must have to consider that in liquid, we assume that the density is constant in liquid, incompressible liquid, okay? But in vapors, what happens that, let's take this vapor is not in a specified form. Like it has a great sense of randomness, and with pressure and temperature, this thing changes. Like we can see in the ideal gas law, PV is equal to nRT, right? So we know that the volume will actually change if the pressure and temperature changes. So what we'll have to consider here is that the density is not constant. Okay, remember this in mind. Density is not constant. Now let's find out the density from here. So PV is equal to some mass upon molar mass into RT. So P into molar mass is equal to M by V RT, and this is nothing but mass upon volume is density RT. So we have a relation of pressure and density. Now if you see that the flow of vapors could be classified into two types. One is throttling and the other is free expansion. The throttling is when there's a sudden decrease in the area like this, and here the vapor comes and suddenly expands. So what happens is that in this throat area, this is a throat area, there are frictional loss, and this frictional loss is that the pressure term moves to this frictional term, while in free expansion we have this pressure term to be moving to more of the kinetic term. That is the difference. Okay, so because we are considering free expansion here, so what we will take is that isentropic process. Now you don't have to actually fear what it is really, so just consider that we have in a particular vessel some vapor. So it has isentropic means entropy, right? Entropy, that is delta S, or let's say this is S1, and there is a hole of particular diameter, and this vapor moves out. It moves out such a way that a system considered as S2. So the vapor moves out in a way, because this is free expansion, so out in a way that this S1 and S2 are same. So delta S is 0, which means the entropy is constant. Why? Because it is allowed free to move, not under pressure. Like it is freely expanding. Here it is first contracted and then expanded suddenly, but this is freely expanding. So the entropy is constant. So isentropic process. So what we can say here, that P V to the power gamma is constant for these processes. As a result, if we say that this V would be actually written like P upon rho is equal to RT by M, which is constant. So P upon rho to the power gamma is constant. We will use this in the further derivation of flow of vapors. Till now, hope everything is clear, the question and this, and please do write the value of this HL in the comment section. If you like the video, please like, share and subscribe.